Good day, guys. It's Friday, our last lesson for the week, and the start of Unit 4. Unit 4 is often called analytic trigonometry. Sometimes it's called trig laws and identities. I like the idea analytic trigonometry because what happens is we're going to start to solve lots of equations, do lots of other, be able to do lots of other things. We're going to really kind of focus on the algebra of trig. So there are going to be all kinds of things hidden in here. Things are going to you'll see algebra that's hidden within the trig, and we're going to do lots of substitutions, manipulation. You'll be kind of surprised as we go through the chapter. So doing this chapter, especially the first half of the chapter, is a big deal. And when we finish the first half of the chapter, we're going to take a midterm. So we're only about 2 weeks away from this midterm. Okay? The midterms are 1 TGA for the year, and it's the one thing you want to be able to do as soon as you can possibly do it. Delaying this midterm will only delay corrections that you can do, and it's a big chunk of your grade. It's 10% of your grade. So you cannot get an A in class unless you take this midterm. All right? There will be no way. No A unless you do the midterm. Okay? So I recommend highly that you keep up with everything we do. It'll be challenging, but the very start of this chapter, I'll slow down just a little bit, and we're only going to work with the learn today, and then we're going to focus some more on some problem types tomorrow. So I'm going to try and introduce all the concepts today, and there's a little practice in the lesson, and I'm going to direct you to your textbook that I've put inside for some extra practice. I recommend the extra practice highly, okay? For me to learn this, I had to do everything. And that means, I was in school a long time ago, 1970s, and, they'd give 30 problem assignments. And I would do all 30 problems. And some of them were repetitious, but some of that repetition helped me to really see how to do things and ingrain the techniques that I needed to know. So don't see repetition as necessarily a bad thing. See it as something that helps you learn the processes. Okay? So here we go. We're going to get started. And for this first part of our unit today, we're going to talk about identities. What is an identity? What kinds of problems can we do with them? And so forth. This is a big deal. In general, when I was in school, I was told to memorize these. The more you memorize them, the better you'll get. However, if you write them all down on a sheet of paper, then you'll have them all available when you need them. And we've talked about this a little before, but now we're going to make it really definite. So here we go. On that sheet of paper, I want you to write the word reciprocal. Identities. And when you write this, you're going to then write the reciprocal of every trig function. So you're going to go sine theta equals 1 over cosecant theta. Cosecant theta equals 1 over sine theta. So notice, for every reciprocal identity, there's a dual, a counterpart. Cosine theta equals 1 over secant theta. Secant theta equals 1 over cosine theta. Tangent theta equals 1 over cotangent theta. cotangent theta equals 1 over tangent theta. So there you go, 6 reciprocal identities. You should write them all down on a sheet of paper. Label the whole paper identity. Number 1 is reciprocal identities. The next one that you should do would be called the quotient identities. Now, the quotient identities and the reciprocal identities you can actually prove. All right? Now, here's a quotient identity. Tangent theta equals sine theta over cosine theta. And cotangent theta equals cosine theta over sine theta. Now, I want to give you an example of how we can prove these identities. All right? An identity is like saying this is a law, this is an equation that's always true, something like that. So how could you prove something like this? So let's do sine theta, or let's do cosecant theta equals 1 over sine theta. All right? So this is going to be a proof. Okay? And the way we would prove this is by definition, okay, so cosecant theta is equal to 1 over y in the unit circle. And that's its definition, right? So we also know that y is equal to sine theta. So we can substitute for 1 over y, we can write 1 over sine theta, since sine theta equals y in unit circle. And so that's it. There's our proof. Step 1, step 2. And if you wish, you could say cosecant theta equals 1 over sine theta. All right? So notice, only one side changes. All right? And you start from something that you know. So this would be like a given, the definition of cosecant theta. And then since we know y is equal to sine theta, we could rewrite this in terms of trig functions only. All right? And that's a basic proof. Same thing goes for tangent theta. If you want to prove tangent theta, you could say tangent theta is equal to y over x, and that's the definition from a unit circle, right? And then you can say step 2, tangent theta equals sine theta over cosine theta, since sine theta equals y and cosine theta equals x in a unit circle, or by definition. All right? And so there's another 2-step proof, a given and then one step to prove it. All right? So that's how you do proofs. So everything above this line up here, let's shrink it down. Everything above this line right here is an identity, and that should be on a separate sheet of paper. All right, separate sheet that lists your identities. These here down below are quickie little proofs, okay, which show you that the identities are actually true and come from something. Okay, let's move on. Let's add to our list of identities, all right? The next thing that comes up is what are called the Pythagorean identities. And so, if it's Pythagorean, that means it's got to come from a right triangle. So we're going to go ahead, we're going to draw the unit circle, and we're going to put a right triangle in there like we did before, and we're going to label the pieces, x, y, and 1, all right? And we know all the definitions of the trig functions from that, okay? Now, the Pythagorean theorem says what based on this diagram? It would say, so write it down yourself, it would say that x squared plus y squared is equal to 1, okay? So therefore, we can say the cosine of theta, where theta is this angle, squared, all right? So if you put the square on the function name, that means you're squaring the function. Another way to write it is cosine squared theta is equal to cosine theta quantity squared, like that. So we tend to write it this way as a little bit of a shortcut. So an exponent on the function name means you're squaring it, okay? And then this becomes, since y is equal to sine theta, we can write sine squared theta equals 1. And so we have a reason for this. Since cosine theta equals x and sine theta equals y. All right? So now we have written this statement right here, cosine squared plus sine squared equals 1, or if you wish, sine squared plus cosine squared equals 1. This is a Pythagorean identity because it comes from the Pythagorean theorem. So again, we'll take that Pythagorean theorem. If you do x squared plus y squared equals 1, and then just for kicks, you divide everything by y squared. Okay? Then what happens is you'll have x squared over y squared plus 1 equals 1 over y squared. So what we know, again, is cosine x and cosine y are, cosine theta is equal to x and sine theta is equal to y. So we can substitute into these things. So this will be cosine squared theta over sine squared theta plus 1 equals 1 over sine squared theta. Well, what we know then is 1 over sine is equal to cosecant. So this is really cosecant squared theta. And then cosine over sine is cotangent. So this is really cotangent squared theta. And this is another Pythagorean identity. Okay? And then finally, the last one is 1 plus tangent squared theta equals secant squared theta. I believe that's right. Yeah. And that is our last Pythagorean identity. So there are only 3 of them, and you should know them. We use them all the time, okay? Now, I want to show you sort of an alternate way to write these, okay? There are alternate ways to write. or alternate ways to look for them, okay? So let me give you a quick example. I'll shrink this up a little bit now. So Pythagorean identities, okay? So let's just look at the first one. We're going to look at cosine squared theta plus sine squared theta equals 1. So one of the things I could do is I could rewrite this as sine squared theta equals 1 minus cosine squared theta. Okay? And then now I notice 1 is a perfect square and cosine squared is a perfect square. So this really mimics our algebra phrase expression a squared minus b squared. This is really a difference of squares. Okay? So I could factor it. So I could say sine squared theta is equal to 1 minus cosine theta times 1 plus cosine theta. And so here's a Pythagorean identity in kind of a different form. All right? And it comes from using the idea of a difference of squares. So one of the things we want to get good at is we want to begin to recognize that we can rewrite these identities as other expressions, or that these identities will look like different things. Okay? All right, let's get ready and go to the next list of identities. So what that leads to are some problems that we have sort of touched on before in Unit 1, but we're going to do more specifically now. So one example of that is somebody may come up to you and they may say, okay, the sine is equal to negative 5 thirteenths, okay? In previous lessons, we would just say, well, what would then all other 6 trig functions be? And what we would do is we would take the sine, we would draw this triangle in an appropriate quadrant. So since the sine was negative, it has to be 3rd or 4th quadrant, all right? And so we'll go to the 3rd quadrant, and we draw the triangle. So this is negative, or excuse me, the sine is opposite. So this is negative 5 down, and then the hypotenuse is 13. And then if they told us this was the sine of negative 5/13, and they told us it was in quadrant 3, then we would draw it in quadrant 3. So then we do the Pythagorean theorem to find the missing side here, x. So you'd have negative 5 squared plus x squared equals 13 squared. And that would give you x squared equals 144, which would give you x equals plus or minus 12. And so the question then becomes, is x a positive or a negative? Well, the geometry tells me it's negative because I'm going that way. Also, the fact that this is in quadrant 3 tells me it's negative. Okay, so the answer I would choose is the negative 12. And now, since x is negative 12, if I want to know what tangent of theta is, then tangent of theta is going to be the opposite over adjacent, or negative 5 over negative 12, which is 5/12. And so you're going to work through problems like that where they give you the quadrant. Now, there are quite a few excellent examples of these in your lesson. So go through the learn in detail and see how they start off in one place and then they'll find another trig function. And then what's it like if they give you the quadrant or they don't give you the quadrant? If they didn't give me the quadrant here, then I could have had either a third or fourth quadrant, and then x equals 12 or negative 12 would have been true. So tangent theta would have been either 5/12 or negative 5/12 because the sign could switch on the 12. So by telling me the quadrant, they make it very specific. So that's the kind of thing you really want to look for in this lesson. We'll probably do some more examples of these in class next week so that we get some more practice on them. And I'll do more examples for quizzes as well. But in the meantime, go through the learn. Don't be somebody who doesn't do what you're supposed to. Watch this video, do the learn, okay? The next thing that you do with trig identities is you just try to simplify an expression, okay? And so they gave a couple of examples, and then you want to look at them, and I'm going to use one of those examples right now. So let's... one of the examples that they gave was this. Suppose you have cotangent theta, tangent theta, plus sine theta, secant theta. Okay? So the big question becomes, can I simplify this a little bit? So one of the ways I can do this is I could rewrite this all in terms of sines and cosines. So cotangent theta by the quotient identity I know is cosine theta over sine theta times tangent theta, which by the quotient identity is sine theta over cosine theta, plus sine theta times secant theta, which is 1 over cosine theta. Now, when I re-look at this, look, these cancel right here. So I am left with 1 plus sine theta over cosine theta, which is equal to 1 plus tangent theta. I reuse the quotient identity. So what we have done is we have simplified this expression into another expression. And we use identities, and in this case I use quotient identities and a reciprocal identity to rewrite the expressions, and then some things would cancel. So the real trick to this, just so you know, is you kind of look at these things and you go, oh, wait a second. Cotangent and tangent are reciprocals. So if I rewrite them in sine and cosine, I'm going to see the things that cancel, right? And then here, I already have a sine, so if I change secant to cosine, I'll get a sine over cosine, which again is a reciprocal identity that I can rewrite. So sometimes you see these ahead of time. Sometimes you just kind of start and work your way through. So what you're doing is you're using identities to rewrite expressions. Sometimes we call it, in this case it's probably simplified because I had 4 trig functions up here and now I've written the expression with only 1 trig function. So that is more simple, right? But we can use identities to rewrite expressions. So finally, the last thing that we have to do, I want to go to a new page and then we'll work on that. The last thing we have to do is what's called verifying trig identities. Excuse me, nose is a little stuffy tonight, I think. All right, so verifying a trig identity. Now, this is what I did, and I called a proof earlier. I had a couple of simple identities on slide 2, and I proved that, what was it? Cosecant theta is equal to 1 over sine theta. All right, I went straight from the definition and I proved it, okay? And so a trig identity is really a proof, but it's a lot like what we did on the previous page. It has a lot of sort of simplifying characteristics to it. Now, in your lesson, they're going to give you a list of things. They give you a list of 6 things, which is what are your best strategies for verifying a trig identity, okay? What are your best strategies? And they list them. Number 1, rewrite as sine and cosine, everything. Number 2, if there's a common denominator, or you need a common denominator, write it. Number 3, split numerators. All right, this is where we're going to start reusing all our algebra. All right, multiply by 1. And what that means is you'll make an expression out of trig identities that looks like 1, and you'll multiply it by something. Usually this is to find common denominators and simplify expressions a little. You can factor. Factoring almost always helps. All right? You can do distributive or FOIL. In your textbook, if you go to the identity section, it will have, it probably has 10 suggestions of things that you can do. All right? So what we're going to do then is we're going to verify some trig identities. Now, they do some examples. You want to go through them in detail, okay, and understand the process of what they do. The other thing I would say about proving identities is generally you work with one side, okay? Now, if you try to work with both sides, what you do is you work with one side, and then where you worked with the other side, you bring that over here and do those steps backwards. And I'll show you what I mean if it shows up on an example that I'm doing, okay? So what I'm going to do is I'm going to pause this for a moment. I'm going to grab my trig book, and I'm going to open it up to the page of identities where there's lots of practice. I'll be right back. So I'm back. So here's our first identity, okay? Now, this is a true statement, but I want to prove it's true, which means I need to simplify one side to the other side. Now, the easiest way to do this, and another rule of identities, is you should always work with what looks like the more complicated side. So when I look at this, I look at this side and this side of the equals, and the left side looks more complicated. So that's the one I'm going to work with. And the strategy, since I want to get to cosecant, I already know cosecant is 1 over sine. So kind of the idea I have in my head, I need to change this tangent and cotangent to sines and cosines using the quotient identities. So that's what I do. Here's my cosine theta times, and then tangent is sine theta over cosine theta, plus cotangent, cosine theta over sine theta, okay? Now, all I've done is this left side. So now I go to the next step, And what I'm thinking is I just want to multiply by the cosine theta. So I'm going to use the distributive property. Okay? And when I do that, I get cosine theta, sine theta, over cosine theta. So now this is like cosine theta over 1. I'm multiplying fractions. Plus then cosine squared theta over sine theta. Okay, now that's my next step. Okay, so I'll put an equals here and equals here. So there's my first step, quotient identity. Second step, distributive property. Notice how everything's substitution or algebra. Now, what I notice here is that the cosine cancels. Okay? So I'll rewrite that. So now I have sine theta plus cosine squared theta over sine theta. Okay? And then I go, wait a second, cosine squared, didn't Mr. Ridpath just showed me I could rewrite, I know cosine squared plus sine squared is 1, so cosine squared by itself is just 1 minus sine squared. So I use a Pythagorean identity alternate form, and here's my sine theta, I just write that, and then cosine squared is 1 minus sine squared theta, and that's all over sine theta. Now, since I have numerators added together over a single common denominator, what I can do is I can write that as two fractions. I can split it up. So sine theta plus 1 over sine theta. Now, just so you notice, that's the cosecant theta right there. This right here is what I'm looking for. And then I'll have minus sine squared theta over sine theta. Okay? Oh, I see. Sine squared over sine, doesn't that cancel like x squared over x and just leave me a sine? So I get sine theta plus 1 over sine theta minus sine theta. Hey, wait a second. Sine theta minus sine theta, that is 0. So this becomes 1 over sine theta, which is equal to cosecant theta. I have now proved this identity because I only worked with one side and I simplified it using different identities all the way down to cosecant theta. Now, if you're not sure what's happened all the way or you were just writing it down, I suggest you go back and listen to it and watch it through as well so you see the process. Study the ones they do in your lessons as well. So we're going to do another one. Okay, so here's the next one. So obviously the left side looks more complicated than the right side. Now, what I have, I'm adding two fractions here. So often when I have that and I have wildly different denominators like this, I am going to multiply by to get common denominators. So since I got to multiply this by 1 minus sine v here, I need to multiply the numerator by 1 minus sine v on the top. And then this one here, I'm going to multiply by cosine v over cosine v. Okay? And so that would be how I would do the problem to get a common denominator. We'll see what happens. All right? So in the numerator now, here, you end up with 1 minus sine v times 1 minus sine v. Now, if you're good, you can multiply these ahead of time. If you're not, you just write it out. Plus, and then on this side, we'll have cosine v and that's cosine squared of v, all right? And then the denominator of the whole side will be the common denominator, which is cosine v times 1 minus sine v, okay? Now, it doesn't look like I made it any easier, but what I notice is I'm going to get a sine squared when I multiply, and sine squared plus cosine squared is 1, so that is going to make some things easier. Now remember, you have to FOIL this, right? Do you remember doing FOIL from Algebra 1? Well, now it shows up in Trig, and you got to kind of pay attention to how it works. But when you multiply this out, you're going to get 1 minus sine v plus sine squared v plus cosine squared v over cosine v times 1 minus sine v. Okay? Now, notice I now have a sine squared plus cosine squared. That is 1. And then minus sine v is minus 2 sine v. So what this is equal to is 1 minus 2 sine v plus 1 over cosine v times 1 minus sine v. And now I see that, oh look, 1 plus 1 is 2, and I'll be able to factor the 2. So I got a couple things I can do here. So I'll do 2 minus 2 sine v, and that will be over the denominator of cosine v 1 minus sine v. I could factor the 2 now, so 2 times 1 minus sine v over cosine v times 1 minus sine v. Now look at this. We've basically done it. Remember what I wanted to end up with? I wanted to end up with secant and a number 2. Well, if you look, here's the number 2, and it's over a cosine. So there's my 2 secant right there. Okay? But I need to also notice that I have a 1 minus sine v over 1 minus sine v, so those cancel, which leaves me 2 over cosine v, which gives me 2 secant v. I have now proved this identity. I have turned the left side into the right side. So I've completely proven it. Okay? Now, I love these identities. I got a powerful lot of them here. Let me show you one here. Here's another one you could prove if you want. Just for practice, I won't do it right now. But it says secant theta minus cosecant theta divided by secant theta cosecant theta equals sine theta minus cosine theta. Okay? So I would probably turn these secants and cosecants into sines and cosines, so use reciprocal identities. And then this means divide, so I'd multiply by the reciprocal of the denominator, and then that'll probably work. Okay, I can see a way to do this. I have an idea of what I need to do, and I've just said it to you. You should try this one on your own. It's not too tough, and you'll use reciprocals, a little different than even the other ones we've done before. And so now I'm going to write a very special problem down for you. Okay? It's a problem I just accidentally assigned to my students one day. Okay? And I believe it's this one. All right? I was teaching a trig class at a college, and I accidentally assigned this problem. It's 1 minus cosine theta over 1 plus cosine theta equals cosecant theta minus cotangent theta squared. Now, if you can do this one, you're an absolute expert. That's all I'll tell you. I would not try it, all right? Now, I'm going to make a copy of a document, and I'm going to post that document in the assignment. And I have a list of 102 identities that you can do, that you can prove. Now, you don't need to do all 102 of them. But my suggestion is, if you really want to learn how to do identities, you probably need to do 10 or 15 of these and practice. This one just so happens to be number 54. I believe this is the right one. I think this is the one that I've been looking for it a long time. It might be number 50, but it's somewhere around 50 or 54. It's been a number of years since I've assigned it, so I may have forgotten which one it is. But these are really quite tricky. All right, that's all I'll say. Some of them are tricky. Most of them are pretty straightforward, even though they're a little bit long. This problem, the problem we did before, even though they're a little bit long, they give you a good sense of how to do these problems. Now, my recommendation is when I post these pages of identities for you to do the ones that are orange if you can, because except for maybe number 53. The orange ones that are listed are really good practice. And there's only about 5 or 6 of those. And then if you did 5 or 6 others, then you'd really got it. To get good at identities, just so you know, you need to practice. All right? So you kind of learn the algebraic techniques. Did you notice all the algebra I had to do this? I just look at sine v or cosine v like it's a variable. So I can square it and divide by it and use it as a common denominator very easily. So I want to recommend that you work on these. Okay? That's all I have for you today. We will come back and we're going to work on these tomorrow some more. So I'm slowing down just a little bit here because this is challenging and it takes a day or two and I don't want to go too fast. All right, see you next time. Bye.